Hello friends, today we learn how to use Laplace transform to solve linear differential equation. After learning this topic, students are able to find out a solution of linear differential equation by using a Laplace transform. Before starting example, we go through preliminaries or basics of a Laplace transform. In this slide, we see the definition of a Laplace transform. The Laplace transform is a frequency domain approach for continuous time signal irrespective of whether the system is stable or unstable. The Laplace transform of a function f of t defined for all real number t greater than or equal to 0 is a function f of s, which is unilateral transform defined by f of s equal to integration varies from 0 to infinity e raised to power minus st f of t dt, where s is a frequency parameter which may be which is a complex number. In this slide we see the Laplace transform of a standard function. If the function is a constant k, then its Laplace transform is k by s for s greater than 0. If the function is e raised to power at, then its Laplace transform is 1 upon s minus a for s is strictly greater than a. If the function is a sine of at, then its Laplace transform is a upon s square plus a square for s is strictly greater than 0. If the function is cos of at, then its Laplace transform is s upon s square plus a square for s is strictly greater than 0. If the function is hyperbolic sine of at, then its Laplace transform is a upon s square minus a square for s is strictly greater than mod of a. If the function is hyperbolic sine of at, then its Laplace transform is s upon s square minus a square for s is strictly greater than mod of a. If the function is t raised to power n, where n is a positive integer, then its Laplace transform is n factorial upon s raised to power n plus 1 for s is strictly greater than 0. And if the same function is given to us, but here n is a rational number, then its Laplace transform is defined like this, which is nothing but gamma n plus 1 upon s raised to power n plus 1 for the same condition, which is s is strictly greater than 0. If the function is a raised to power t, then we can easily convert this function into exponential function, and then we get a Laplace transform like this, 1 upon s minus log of a for s is strictly greater than log of a. In this slide we have to take some properties, or we see some properties of a Laplace transform. That is first shifting property, change of scale property, Laplace transform of a derivative. This is a useful property to solve linear differential equation by using a Laplace transform. That is, if the Laplace transform f of t is equal to f of s, then the Laplace transform of nth derivative of f of t is defined like this, where the power of s is decreased in each term, and here this f of s is multiplied to s raised to power n, where f of s is a Laplace transform of f of t. F of 0 means when we have to put t is equal to 0, we'll get the value of f of 0, and so on. In the next slide we see some more properties of a Laplace transform, like Laplace transform of a integration, multiplication by power of t, division by power of t, Laplace transform of a periodic function, Laplace transform of a Dirac delta function, Laplace transform of a unit step function, and so on. So by using a definition of a Laplace transform, if we put a one by one function which is given in above table, we can easily get a Laplace transform of a given function. Also we can easily prove all this property by using a definition and integration. In the next slide we take one example on linear differential equation which is solved by using Laplace transform. See the example. Using Laplace transform technique, solve the following initial value problem. That is d2y by dt square plus y is equal to sine 3t, where the conditions like this: y of 0 is equal to y dash of 0 is equal to 0. To solve this linear differential equation, we can write down this equation in this form: y double dash plus y is equal to sine of 3t with the given condition. By taking Laplace transform and by using the table and the property, that is Laplace transform of a derivative, will get this equation. So by using the property and by using the table, we'll get this equation. By substituting the given condition, that is y of 0 and y dash of 0 is equal to 0 in above equation, and collecting the term of y of s in a one bracket, we'll get this equation. Due to y of 0 and y dash of 0 equal to 0, some terms are vanished and we get this equation. After shifting this bracket on this side, we'll get y of s, which is equal to 3 upon s square plus 1 into s square plus 9 here. Now when we take inverse Laplace transform of this y of s, we'll get easily the value of y of t. Here this y of s is a Laplace transform of y of t. So by taking inverse Laplace transform of y of s, we'll get the value of y of t. There are so many methods to find out inverse Laplace transform. First one is a convolution, by using convolution theorem, by using partial fraction method, by using the formula of inverse Laplace transform. Since we do not discuss any method here, we directly go through partial fraction method, which one is easy due to both the brackets have same degree. So by using that partial fraction method and above formula, we'll get, or we can write down y of s in this form. By simplifying this, we'll get this equation, and by taking inverse Laplace transform on both sides, we can easily get the value of y of t, which is nothing but a solution of a given differential equation, and this differential equation satisfies both the condition, and that's why we solve this differential equation by using a Laplace transform technique. So you can easily solve some more example on Laplace transform by using the formula and the properties of Laplace transform and inverse Laplace transform technique. These are some references to study deeply of Laplace transform, that is Advanced Engineering by H.K. Das. This is the publication. Higher Engineering Mathematics by B.V. Ramana. Higher Engineering Mathematics B.S. Grewal. A textbooks of Engineering Mathematics by N.P. Bali and Manish Goyal. These are the publications here. Thank you very much.